You can see my screen, right?
Not it.
Can you see now?
Yeah,
Huh?
yeah.
So we have seen this LANet and LXNet architectures, right? And then there is VGG 16, and we actually used it and did some transfer learning. I don't know whether you saw the results or not. Let me open that. I uploaded a file. It took around 3 hours, I think 2 to 3 hours. And somehow the GPU was used very less. Maybe because maybe some part of it is Kira's. I don't think so. But
Maybe TensorFlow is also installed, sir. Is that right?
no, I installed GPU one.
Okay.
No, I installed GPU one, I think. I don't know. Maybe I installed TensorFlow.
That could be one of the reasons.
That could be one of the reasons. But yeah, let me open this and see version, and we can check whether it is GPU version or not. So I ran it, and the data set I loaded was not right. From the Microsoft one, right? When I downloaded that, some of the files have wrong extension, so it's not able to read them. So again, I went into Kaggle, downloaded it, and then created necessary folder structure there. I told you, right? There should be two folders for each class, and then should have respective images in those folders, right? So I created the structure and a Unix command, right? You can just say, mv move all those the files starting with cat into one folder, and move all those files starting with dog into another folder. Something like that I did, and then built a model, and we've got 97% accuracy with 2 epochs only. Right, with 2 epochs we have got 97% accuracy. So if you do 10 epochs, right, it'll do very good job. So here I wrote a simple method to make predictions on the production, right? If you have 4 images, maybe I have taken 3 images from dog class. I know that it's in this folder, I have taken it, but in real time you pass these, you get these matrices, right? These arrays you get as the output. Sorry, the image arrays. So first we need to convert this image into matrix, right? So I have passed it. I have taken zeros array of the dimension we wanted, and then in the image list I have taken the image, converted, and then yeah, okay, I am creating a batch here. Okay, so I took a 4-dimensional array here, right? And then I have 3 images here. I don't know how many images will come in production, right? So there may be 100 images also. So to combine all these 3-dimensional arrays, each image is a 3-dimensional array, right? Each image is a 3-dimensional array. If you say image dot load of whatever image, it will be 3-dimensional array, right? So I expanded dimension and then appended that to this return array. Okay, I expanded the dimension to 4-dimensional array, and then appended that to the zeros array, and then the first array I deleted. So for the zeros array which I created initially, right? The structure is going to be, once after you ran this for 3 iterations, first array will be zeros array of this dimension, second, third, fourth are going to be these No, these pictures arrays, right? Understood?
No, sir, actually.
Okay, give me 1 second. Let me draw this and explain.
No.
Okay, so let me draw this and explain that. Right? So these kinds of things we have to do in TensorFlow or whether you use PyTorch also. Most recently, I found PyTorch more interesting than TensorFlow because those guys adopted the cafe model, which is very fast. Now, when you are doing computer vision projects, right? I we found that the PyTorch is faster compared to um, TensorFlow. So we are actually using PyTorch for the speed detection. So what I am doing is here, right? This method's whole purpose is to create a batch of images to pass it to the model. So we know that the model is taking a three-dimensional array as input, right? This dimensionality is what it is taking as input. We know that, right? Do we?
Yeah, yes, sir.
Right. So when you are passing 4 images, what will happen? This is going to be 4, right? Yeah, 4 comma 224 comma 224 by 3. Or in NumPy it is going to be 4 comma 3 comma 224 by 224. But the dimensionality is taking like this, so we created array like this. So whichever way the model expects, we need to send the data like that, right? So in production, you don't know how many images are going to be there. In production, we have 3 images here. Okay, fortunately they are dog. I took it intentionally, but in right, suppose that there are 3 dogs, right? So I need to create a 4-dimensional array where, right, each box is a dog picture. Suppose that each box is a 3-dimensional array of a dog, right? Right. Now you need to enclose everything into another brackets or box, right? So to do this, what I did initially, I took a zeros array, right? Zeros box. These are all zeros, okay, of this dimensionality, okay. And then I'm loading the image, converting that into this dimensional array, and then expanding the dim so that it becomes a 4-dimensional array, right? 1 comma 224 comma 224 by 3 it becomes, right? And then appending that to this model. When you append, right, it will come as second one. This is the original. This is the first dog image. Okay, second dog, right? And third dog. So we have got all 3 got into the array, right? Now what you should do, you should remove this because you created this to get a structure there, right? Now I removed this, right? See, deleted this and then returning it. Got it? Now we got this structure. Got it?
Yes, sir. One second, sir.
Yeah, please.
So where the dimension is actually changing from 224 by 224 in by 3, where the channels are coming. When we are
This,
loading the
right?
image, okay.
This is actually low. So you see, target size is 224 by 224, Right? You specify you whether you specify the channels or not, it will actually load. You by default in this method the channels are 3 default value.
Okay. Channels are 3. Okay.
Okay. Expanding dimension will become, we'll add this one, and fourth dimension it will add.
Sir, by default, sir, expanded dimension means is by default it will take one, sir.
One only.
Okay.
In the additional, if you call this method one more time, right, it will actually add one more.
One more.
One,
Yeah, yeah.
it is 5 dimensional then.
Yes, yes.
Right? NumPy, we actually try to understand this, the multi-dimensional stuff, right? That is useful here, very useful here. Got it? Can I move on?
Yes, sir.
Yes, sir.
Okay, so this is how the data actually came out when I called. So I created a batch now. This batch is eligible to pass into the model. See this 3 by, if I pass 4 images, right, it will get 4 here, 10 images, 10, right? So 100, 100. So this is constant. This image structure is constant, but this dimensionality is the batch dimensionality, right? Process input, I don't know. There is nothing much to do process here, but in VGG 16 there is a method called as process input. Let us see what it does. VGG 16 process inputs right here. Oh, this is capital VGG 16. In this they changed it. In previous version, right, it was there. Oh, see this. This is the one I was using, not this one. Right, process input. Yeah, and then. Process a tensor. What process it does? The floating point numpy array are the tensor to 3D, 4D with 3 color channels with values in the range of whatever. The processed data are written over the input data. What process it does? Process numpy. The image are converted to RGB. Then each color channel is zero centered. Okay, with respect to the ImageNet data set. Okay, okay. Without scaling. Without scaling, zero centered without scaling. Okay, they are actually taking mean of all those all those numbers in the array and subtracting them from the data, right? Mean centering, right? That may be needed for the ImageNet. ImageNet guys would have did that processing before they passed it to the VGC 16. So we need to do the same thing. So process input is actually doing that. Got it? Mean centering the data. Got it? If you don't do mean centering, right, again model may not work well. Got it, right? Understood?
Yes.
Yeah. So I did image processing. It's just a call. And if everything is right and the structure is right and data, the numbers are in each channel, the numbers are between 0 and 255. It will not throw any error. Centering will happen. And now I loaded the model. I saved the model here. Right? Now I loaded the model. Right? This is like production, right? And then predict. I passed the whole array. I got scores like this. See this? This is 1, right? Probability 1. This is like 0, almost 0, right? The argmax is going to give you the classes 1. So when I passed cats, right, I got zeros. So it is predicting correctly. Right? I'm actually checking whether it is predicting correctly or not using. So this is how you do, the predictions, right? Training is one way, and then you need to create the batches and format the data in same way as we trained, and then you need to pass it and it will predict. Got it? Any questions here? Okay, good. So that is VG16 and the transfer learning, right? I think today's class is very important. We are actually dwelling deep into the other kinds of networks. These guys. Yeah, maybe I'll send a message or call them and let them know. So now we know convolutional neural network and deep neural network. With these networks, right, we can create different kinds of logically complex networks. Okay, so you can create a network like this. Where is that? Yeah, you can create a network like this, huge network, right? Input, and then there are 1,000 layers or maybe 100 layers, and then the output, something like that you can create. But the problem with that is, right, in theory, right, in theory, when you make the model too complex, the model should work well, right? On training set, not on test set. Now we are not talking about overfitting. When you have a huge network with more layers, the error should reduce. But what happens is beyond certain number of layers, the error starts raising even on train set, right? So suppose that you did 50, maybe five layer network, error reduced to 10 layer, 20 layer, right? So you are experimenting, incrementing number of layers and experimenting. 20 layers, it worked, well, right? But from 25th onwards or 21st onwards, the error started raising. Right? This is the reality. So in reality, when you make too complex network, error will raise. Maybe because of the exploding gradients or vanishing gradients, right? So you can avoid that by choosing the weights appropriately. That is one solution. But the other solution is skip connections. Okay? We are trying to understand another solution to solve exploding and vanishing gradients problem. Okay, so this is called a skip connection. Let us look at the theory here. In theory, the number of layers increase, error will reduce. It's not true in reality, right? With the number of layers increasing, the error will increase as shown above. This happens due to vanishing or exploding gradients, right? This can be this can be solved, partially solved using choosing the weights appropriately and doing gradient clipping. You remember gradient clipping? Do you remember gradient clipping? Do you remember gradient clipping?
No, sir.
Yeah, the thing, it's like there is a function called as a clip. I showed you somewhere, right? Let me show you.
Cannot recollect actually.
Yeah, that's fine, sir. That's fine. Too many concepts, and unfortunately, I am taking classes in the weekends and people are not attending. That's another. So yeah, but this is how it is. You need to practice and where is that file? I gradient clipping. I did exploding vanishing gradients. Momentum somewhere here. Do you see exploding vanishing gradients file somewhere? Oh, let us see. Maybe somewhere here. Clip pivots. I'll explain. I'll explain. Before that, right? I wanted to show the code example and then I'll talk about it. Hey Rama. Let me go back. Okay. Give me 1 second. Let me go back to repository and then show you that. I think I should copy paste that theory somewhere. Give me 1 second. See, yeah, this is the one. See, while reorganizing the code, right, I kind of left out some in the 1.14 thing. So yeah, if you see this, right, when you call the optimizer dot minimize function, right, when you look at this code, right, we are saying compile and fit, right? In the 2.0 code, we are compiling the model and then saying fit. But in our old code, right, in our 1.14, 1.15 code, we used to write this much of code, right? We need to create an optimizer and then we need to call a function called as optimizer.minimize. That function, right, internally, when you call fit, right, that minimization is already being called on this optimizer. Why am I calling minimize on the optimizer? What is optimizer? Do you remember?
To converge.
To converge, right? What is optimizer? This SGD or momentum, RMS prop, Adam, these are all optimizers, right? The Adam, momentum, and RMS prop are the advancements or little tweaks to SGD to converge faster, right? You understand the pattern in which it is jumping around, the theta is jumping around using exponentially weighted moving average formula, and then try to calculate it upfront, right? Or calculate it using the current gradient and the previous gradients and jump, right? That is the optimizer. Those are the optimizers, right? And on optimizer, the algorithm will always call minimize function. When it calls minimize function, right, internally it is calling compute gradients, right, which is nothing but back propagation, right? And then it is actually applying those gradients. What is it? What is the applying gradients? It calculated derivatives here, and then it applied it onto the weights. Okay, so that is the training.
Calculating new theta, right? New weights.
Calculating new theta. When you say apply gradients, it is calculating new theta. This is just calculating gradients. Gradients and variables. Their variable names, right? So these gradients you can actually clip them in a range, right? So in 2.0 the function is just clip. Okay, clip by value you should say, and take gradients, right? In a for loop we are taking all gradients and putting them in between a threshold, right? -1 and +1. In 2.0 we are saying tf dot clip and then giving 1 or 2 or 3. It is taking -2 and 2. If you give 2, it will take -2 and 2, right? Threshold value you are passing, it is taking the range, minus and plus range, and then clipping the values. Clipping the values means it will try to bring all the data, all the gradients into that range. How can you do that? Min max scaling, if you do, it will come down to that range, right? Whatever gradients you have, it is applying min max scaling kind of normalization, and then bringing all the gradients into that range. Now what happens? Your gradients are small, right? Your weights will get adjusted, accordingly, right? W is equal to W minus alpha into whatever, right? So your weights will not explode. Initially you chose very small weights, right? Very small weights between -1 and +1, and they're close to -1 and +1, right? That way you chose, and now you are actually making sure that every iteration, right, the gradients get calculated in that range only, and in a given range only. Then what happens? The gradients will not explode, right, or vanish, because they are actually close to 0.999 kind of a thing. Got it? That thing, that is called as gradient clipping. Okay, got it? Any questions?
In short, all the values will be recalculated into a range of threshold.
That's it. In short, gradients will be, even when gradients are going beyond the limits, this gradient clipping will actually control them not to go above that range. That way, total weights will stay in a predictable range rather than going into zeros and infinities. Got it?
Okay.
But this is one of the important questions in interviews, and we need to understand also. Okay, that is gradient clipping, right? So we can use gradient clipping not to make the model explode, but the model's performance may get damaged because you are always trying to intervene in the process of understanding pattern, right? You are trying to tweak weights, so you are trying to intervene in the process of that neural networks or whatever, right? So that's maybe one problem, right? It's a black box, you don't know, right? That may be one problem. Maybe the model is not working. To avoid that one, right, you can use skip connections, a concept called skip connections. So exploding vanishing gradients can be controlled using two approaches. One, taking the weights close to 1, right, 0.99 kind of a thing, right? And then second thing is, on top of it you take gradient clipping. It will stay in the range and it will not explode or vanish, right? Those are two things that we can do. The third thing is resnet. We call it as resnet, or a skip connection, we call it as. Okay, so the skip connection works as a identity operation, right? You take AL, some layer, right, some layer, AL layer, Lth layer, right? And you are calculating ZL. That is nothing but you have some weights here. You multiply these values and you get the linear combinations, and then you are applying ReLU. You got AL plus 1th layer. Okay, and then on the AL plus 1th layer you are applying again weights and you are calculating ZL plus 1, right? ZL plus 1, right? On that again you have weights and you are calculating AL plus 2. That's the normal network, right? This is a residual block, we call it as. On a huge residual network, I took one block there and trying to explain how exactly it works. Okay, normal network is like this, where beyond certain range the model is unable to understand, right? This is the residual network, Resnet 50, Resnet 101, Resnet 102. Those are already pre-built models, okay, pre-trained models. So this is the architecture of that. The main motto here is, the main motto or um, the way the algorithm solves is, suppose that one, two, 1, 2, 3, 5. So there are 10 layers here. Suppose that the algorithm learned what it need to learn by this layer, 6th layer. Okay, then then algorithm will make all these layers in such a way that they will not add any understanding to the outcome. Okay, the resonance main purpose, right? Even when you have 10 layers, if the algorithm learned something by 6th layer, it will make the rest of the layers as identity layers, so that it will not add any intelligence to the model. That way, the model will not diverge. That's the motto. That's the basic understanding. Mathematically, how it happens, I'll explain in a moment. Okay. Did you get that concept? Theoretically, did you understand? Theoretically, you understood why we are looking into this? No? Okay, I'll come back to this. I have kind of 20 minutes here, so I'll come back to this. So, don't look at this orange line first. Just look at AL plus 1 and AL plus 2. Did you understood what is happening here? Don't look at resonant block and residual block and this orange line. You understood, right? What is happening there?
This is actually its own way of having a network, right?
No, that's the point. So if you don't look at orange lane.
Yeah, an orange layer is not, I'm not looking at, but it is actually calculating the linear combination and applying ReLU. Again, linear combination.
And ReLU, right? This is normal,
Deep neural network.
Deep neural network, right?
Yes.
Okay. In that deep neural network, if you add a skip connection, what is skip connection? Before calculating linear combination, right? This outcome, whatever AL, we're actually connecting it to AL plus 2, AL plus 1, one's output, right? So AL plus 1's output, we are actually connecting. So here there are 3 nodes, right? We got the 3 linear combinations. Along with those linear combinations, we are actually adding this also, appending this also, and trying to pass it to the AL plus 2. That is called as residual block. Okay. So you can pass it, right? So, how can you pass that? In a neural network, right? Here I added maybe a model class will work. I showed you model class example. Right? See, in this model class, what we did? We did something here, right? Hidden 2, hidden 1 we did, and then again we actually took auxiliary, and then hidden 2 we actually connected at the end. You can do that, right? Did you understand what I'm actually trying to say? You can actually do this with the the TensorFlow code using model class. Got it? Things are getting complex, right? Got it or not?
Yeah, this code actually fine, sir.
This code is fine, but why did I show this code? Because you can do these kinds of networks manually. Whatever architecture you want to design, you can design that, right? So here,
Yeah.
what I'm going to do is, I'll take this output and append it to this layer's output, this layer's linear combination output. Before I apply ReLU, I'll add it, I'll append it, and then apply ReLU.
But so one second. The terminology and what is happening is bit opposite. When we say skip connection, I was thinking these actual values will go here and directly ReLU is applied.
These values, right?
Yeah,
These AL
values will be taken
will go here, and then ReLU
ReLU is applied.
But they are it happens like that only. We will see that in math, right? It happens like that only. The resultant output is going to happen the way you thought of. It will actually kind of create a this layer as a identity layer. It will make when you actually add the skip connection, right? Automatically the neural network will make it. Even though you are adding these ZL plus ones, it will not consider them. Okay, so your thought process is right. Skip connection means it is trying to skip a layer. Okay, basically, okay, at a high level if you speak. Okay, I'll show you the math and then come back to that diagram again. Okay, so this is a neural network, right? Resnet, a big, huge neural network. At layer AL, I'm actually adding a skip connection like that. So in diagrams they show like this, but it is actually happening like this. Okay, so how it works? Suppose that by layer AL, network learned everything that it needs to learn. So by here, right, it actually learned everything. That means the outcomes of this AL are actually matching very close to Y. Suppose that, right? In this case, AL plus 2 must be equal to AL, right? Whatever the outcome you are getting here, here also you should get the same output. That's the goal. Okay. Mathematically, how can you do that? Skip connection can do that. Okay. In other words, AL plus 2 must behave like an identity function or AL also. And so it's like all the layers in between, right? They should work like an identity function. So residual block, acting as identity function. So when you actually add the skip connection, right, what happens? AL plus 2 is equal to ReLU of ZL plus 1 plus AL, right? AL plus 2 is equal to ReLU of ZL plus 1, the linear combination of L plus 1 and the AL, right? Okay. So if WL plus 1 vector becomes 0, right, on regularizing the network, if WL plus 1 becomes 0 on regularizing the network, what will happen? ReLU of AL is going to be AL, provided AL is greater than 0. Right? If AL is less than 0, you would have got 0 here, and here also you will get 0. Got it? Now AL plus 2 is equal to AL. So in a neural network, if you add this connection, right, it actually makes this happen. The weights associated with AL plus 1 will be made 0. It's a regularization effect, because the network already learned what it need to learn here, and when the cost function looks at it, it understands that by here it actually learned, so it will make the weights of this layer kind of 0. That way it will kind of this layer is not there at all actually, right? When you actually make weight 0, all the outcomes here will vanish, and then you're adding AL plus 1, so the weights will be chosen in such a way that AL plus 1 is being outputted, right? So there is no linear combination basically. So whatever AL plus 1 you got, you actually passed it there. So it is AL plus 1 only. There are no weights associated with AL plus 1. Only AL. Only AL plus 1 has got weights. Do you understand?
Sir, one question. So basically, this is nothing but dynamically learning that by AL itself we are good. So
Yes,
that
and
dynamically do the skipping. Is that what it
yes,
is?
and yes, yes. See, in a neural network, that's a very valid point, and you got it right. In a neural network, you don't know what is happening behind the scenes or internally what calculations are happening. They're huge networks. What we do in real time as a developer, right? We may not do that big of a neural networks, but the Google guys and the Facebook guys, these guys do have huge neural networks. We don't know what is happening there. If you have these kinds of mechanisms and you have 100 layers, maybe by 10th layer, if it learns, rest of the layers all will become the because of the skip connections, those rest of the layers will act like identity function. Identity function means matrix into identity is equal to matrix, that's it. So by 10th layer it learned, and rest of the 90 layers it's going to be kind of identity only. You get that 10th layers outcome as the outcome, and model works well. Got it? I think you got it. Sorry. Yeah. Any questions? So regularization kind of thing it is. In our linear regression, logistic regression, right? What regularization does, this thing will do that.
So when skip connection is applied, it actually tries to make the WL plus 1 vector to 0.
When it already learned something somewhere, in between.
Yeah, if it is already learned at some stage in the network, and the network is continuing, and then it is identified that, okay, whatever we learned at some stage n, and stage n plus k is not required, then it applies this skip connection at stage n.
Yes. No. It is not going to apply. We need to design that. We need to, while writing the code, you need to write the skip connections also. You need to write. There
the
is
position also we need to.
There is a block called as residual block. You can use that block. It will actually create this kind of connections, right? Network residual block, residual block, residual block, residual, like that it is. You can manually also create. Maybe you want to skip 3 connections at once. You can actually do that using model class. Right?
Okay, where to skip is also manually controlled.
That you need to play with.
Okay.
Generally, research found that this kind of residual blocks worked well. These are predefined, pre-built, blocks they are. Okay. Got it?
So maybe example code, if we see, maybe we'll have it better.
I did not write any example code here, sir, but in the applications, right, there is Resnet. Resnet 50. You can use that. And from the same dog cat dog classification, right? You can use this. Try to experiment with that, and then if you have any questions, come back. And in that the network structure is like this. Okay, if you want, you can create your own also. If you want to do that, you should be doing it like this. Not a big deal. Not a big deal, but it takes time. You need to play with it a little bit. And this model class to create models is to give you that flexibility of doing very complex neural networks. And in the NLP, right, the exercise I have is around this model class and lambda layer and all that. Okay. So I'm kind of trying to give you a hint that you need to practice a little bit on this model class to kind of practice a little more on the exercise I am going to give. It's not a simple one, but we should practice those kinds of things only. Then we'll get more confidence to handle the real time. So that is residual net. Okay. So Resnet 50 means there will be 50 residual blocks, I think. In total 100 layers, I think. So just look at the API documentation, you will understand. So there is one more point, 2 more points we need to understand in residual blocks. If you are trying to build, if already the network is there, no need to worry. If you are trying to build it with model class, right, you need to be careful with these 2 points. Resnets in Resnets, all layers must be of same convolution or same size. If it is convolutional layer or deep neural network, it should be of same size. Okay. The reason behind this is the math involved in calculating this, right? To perform the ZL plus 1 and AL must be of the same size. So you are what you are doing, you're actually adding these AL values, right? There are three values here, and you took I said concatenation, right? Sorry, it's not concatenation. It's a broadcasting, right? If two matrices are of same size, right? There are two wectors of size 3. When you do this sum, what happens? It becomes one vector, right? It becomes one vector. Okay, the W's will be chosen in such a way that the AL only stays and ZL will not stay. I actually took a extreme example of weights making 0. It's not going to make weights 0. If you look at this, right, it's a broadcasting concept. Two matrices or two vectors are being added to each other. To add two vectors, the size of those vectors should be same. Right, when you added two vectors, right, you got AL plus 2, but if you make W 0, right, the whole thing will become 0. So you need to have weights in such a way that only AL remains and whatever ZL plus 1 is going to vanish. So I took an kind of extreme example here, extreme way of explaining it here, but you got the point, right? I confused you, or maybe I got confused a little bit by saying concatenating, right? Got it? Got the point?
Yes.
Okay. So, sorry for the confusion, but basically it is a broadcasting thing, and then the W's will be a ratio that actually outputs AL, and tries to vanish whatever the additional ZL plus 1 got added there. Okay. So if AL and AL plus 1 are of different dimensions, right? There is some math you can do. You can actually add one more weight parameter to do linear combination of AL to reduce or increase the size. If ZL plus 1 is of different size and AL is of different size, then you can actually do a matrix multiplication, right? So if this is like, I took like, AL plus 2 is 256 rows and AL is 128 rows. You take 256 by 128 matrix, a weight matrix, and then multiply that with this, you will get 256, 256 by 1. You multiply these two matrices, you multiply this weight matrix with this matrix, you will get 256 values. Then you sum 256 and 256 and the calculation happens. Rather, it will throw error, dimensionalities did not match and things like that. The simplest thing is that same size convolution or deep neural networks. Okay. So that is residual net. Okay, Resnet we call it as. Okay. So we'll stop it here, because Seshiram need to leave, and tomorrow we'll talk more about pre-built networks, because we are not going to do experimentation on these because our machines are not not capable of handling it. If you look at this models, I tried to use XLNet. Somewhere XLNet is there. See this XLNet, exception net, sorry, exception net or XLNet. So I tried to use this, and my machine has 32 GB of RAM and a GPU. It failed. It did not run. Right? It said after 2 minutes of execution, it said out of memory. So to execute these kinds of huge networks, right, you need big servers or machines. But theoretically, we should understand what's happening behind the scenes, because these kinds of networks, more networks will come in future. Okay. So tomorrow I'll explain these little concepts about inception net, maybe 5 minutes, 10 minutes thing, and then we'll jump into computer vision. And by Monday, right, we'll be in a position to do some object detection, exercise. I would recommend you to do that exercise. It is very simple. I'll show you the resources and all. It is just that you need to spend time and you need to have a Unix machine, or you need to work on Collab, either Collab or a Linux machine. Okay. So we can work on Collab. So 9th, 10th, 11th, you work on object detection. I'll make you, capable of doing it by Monday. Okay. who Girigar, your friends, right? Let them know that don't to watch videos today, tomorrow, and it is very important, very important.
Sure, definitely.
Whatever